with Graciela, Gelmini, and Pedro Machado. So just hand the microphone to them. And if you have questions, I will try to circulate the microphone. I mean, you will have questions for sure, and we'll try to circulate the microphone.
I can use my lecturing voice, but no, you need to record or whatever.
Yeah.
Or one of you can keep
No,
this.
that's okay.
That's okay. Eso funciona, sí. ¿No? Qué raro.
Esto no
Dejamos esto por ahora.
Y bueno. Sí, pero lo puedo usar así.
Hola, hola. Yes.
Hay que prenderlo. Bueno, sí. So the idea is that you will ask questions, but it depends on him, on me, on whatever, cosmology, dark matter, neutrinos, life related to career-wise, no? Otherwise, it becomes too wide. But so this is an attempt. Otherwise, the alternative would be to assign some problems and then discuss problems or something like that, which is also a useful use of time. So it depends on you, right? So if there are questions that you want to start with. Yes, there are, yes, sorry. Should I decide? Because I just decided. Okay, so that's...
Thank you. Regarding the UPMNS matrix, could you explain a little bit regarding the names that each term has? Like a term has, you said that each term has a name because it was discovered like in reactor, in solar neutrinos, and...
Oh, yeah. For the mixing angles.
Please.
Yeah, so the PMNS matrix goes like this, and I'll just do like U23 for a rotation, the 2-3 plane. I can say V13 for a rotation, the 1-3 plane with a phase, and this in the 1-2 plane. If you go a little bit deeper into that oscillation probability that I gave you and start plugging in like cosines and sines of the angle and the delta m squares, etc., you see that for if you have MEV neutrinos at distances of 1 kilometer, and I'll cover that a little bit more in my second lecture, but just to give you a feeling, you get oscillations driven by the θ13 term. The experiments that can do that are reactor experiments, like, for example, Diabei in China. If you go to higher energy, say GeV, and you look at 1,000 kilometers, you actually get oscillations from, so this is usually nu E to nu E. That's what reactor experiments can see. Here you can have, for example, nu mu to nu mu. At the GeV, 1,000 kilometers is driven by delta the θ23. So that is actually how we discovered neutrino oscillations using atmospheric neutrinos. So the names of the mixing angles, names, they're not really official names. They really come from how we discover them or how we better measure them. So θ23 is called the atmospheric mixing because it's what drove atmospheric oscillations that led us to discover neutrino oscillations. θ13 is well measured in reactor, so reactor mixing. And θ12 is actually quite sensitive. It plays a very, very big role for solar neutrinos. So we call it the solar mixing angle. But that's essentially it. So next lecture, I'll cover experiments a little bit more. I'll not cover in great detail because I think next week Dan is going to cover experiments in great detail. But at least we'll give you like how we produce and detect these neutrinos and which mixed angle and mass splittings are relevant for them.
Somebody...
Hello. Okay. Professor Graciela, I have I don't know if you're going back to the quantum fluctuations, and I would like to know if we know for sure what kind of quantum fluctuations were responsible for the, for example, say the cosmic microwave background that you said.
So this is inflationary models. Well, there is a whole industry of inflationary models. So the basic idea is, for example, to have one scalar field. Of course, scalar fields can account for many things. It's not, I mean, this is a macroscopic, sort of a macroscopic description of something that can be very different. So, for example, the Landau way of describing superconductivity that in the end ended up being, Cooper pairs, this field that actually is responsible for the actual phase transition from normal to superconductivity. So this is a description that in principle is a macroscopic description, simplified description. And so what you have is a scalar field that has a particular, rather arbitrarily chosen field that produces inflation, but it has to produce also an exit from the inflation. And there are several different ones, but one of them is something like this. Right, so this is the potential, and then this is the field, and it looks something like this. So this is, for a very long time, a phi dot and even phi 2 dot are very small, and one has to quantify where it is. But they are not zero. So if the initial conditions set up your field somewhere here, for a very long time, this potential is fixed, and essentially this acts as a cosmological constant. So this is the basic idea. But then there are quantum fluctuations, right? So quantum fluctuations in the field, so there are also approximations in these quantum fluctuations. So usually what you separate is what happens at distances, scales larger than the Hubble. So the Hubble constant, or the Hubble length, h to the minus 1, is the one at which the velocity of the space-time, let's say, going out, is c. So at distances much smaller than h to the minus 1, you essentially can use quantum mechanics, as you know, at distances much smaller. And then you use, at distances larger than h to the minus 1, this is cosmology, and then you make contact with cosmology. And the passage is not very smooth. There are some approximations that you have to make. And then for the rest, there are quantum variations. So if you have quantum variations, I cannot compute them. I just tell you I mean, if you want, I can say more about that, but I have to look it up, because otherwise I cannot. But for example, this, so at some point, when the field reaches here, it finishes, right? The inflation finishes, and here you have to make some way in which the universe is repopulated, because of course its expansion of the universe is exponential. Whatever was there before is diluted, is exponentially diluted. And then, so you can, for example, one way that you can see is that there will be small quantum fluctuations that lead the field to be a little bit to the right, a little bit to the left, a little bit closer to the end, a little bit not closer to the end. So in last instance, as the field evolves, following this, and one says, of course, that the field rolls down. I mean, this is because one makes an analogy with a little ball, because the equations of motion would be the same as if I would be a little ball here, and through gravity, it will evolve like this. And you say the field rolls. But the evolution is the same as if you would leave a little pebble here and it goes down. So in some regions, small regions, the end will happen a little earlier or a little later. And so the production of particles will be a little bit different in different regions. And this generates a difference in density, essentially is this. But so here, these differences, of course, are expanded because even when there are small regions here, but the whole region is expanded, exponentially expanded. So it becomes outside the horizon. H to the minus 1 is not the true event horizon. There is an event horizon. This type of space is called the Sitter space. And there is an event horizon, which is much larger than H to the minus 1. That's why you can go out. Now, when the universe becomes radiation dominated, H to the minus 1 is now the horizon, that we call the particle horizon. There are two different things, event horizon, particle horizon. And so all of this went out of the horizon, and then they re-enter the horizon. So the idea is that there is this fields, if this is the scale factor of the universe, and something like this, and these are scales. Essentially, these are scales. So this is H to the minus 1. This is a scale. And then at the end of inflation, you have that actual H to the minus 1 changes with the scale factor. This is radiation domination, and this is inflation. And so these inhomogeneities that have a particular distance when they cross the horizon, H to the minus 1, go out of the horizon, expand, and are enter into the horizon at different stages. So this is the general idea of this. I can prepare some more if you want, but this is the general idea. So quantum fluctuations become inflated away. They come outside the horizon. In what will be the horizon is H to the minus 1, essentially, will be the horizon during radiation domination. And they are encompassed by the horizon, essentially. H to the minus 1 is 2 CT or 3 CT in radiation domination or matter domination. So one always says CT, right? But it's 2 or 3 times as much. And so they are encompassed by the horizon. And there is an evolution outside the horizon. Now, there is something important. And this is the last thing I will say. When they re-enter the horizon, this is the moment of horizon crossing. The spectrum at horizon crossing, it has been measured, actually, to be practically a scale invariant, namely delta rho over rho, the magnitude of the density inhomogeneities is the same at horizon crossing, independently of all the scales. And the way of interpreting this is the following. The Sitter space, which is what happens here practically, if this would be exactly constant, it will be exactly the Sitter, is approximate, essentially is time invariant. Time invariant. And so inhomogeneities that come later or sooner respond exactly to the same physics. And so delta rho over rho is the same when they leave H to the minus 1, which is also the same for all of them. And therefore, it's the same when they come in. And this also is something that reinforces the validity of this idea of having inflation, because it has been measured by Planck, et cetera, that the spectrum at horizon crossing, because this is not at a fixed time, because each inhomogeneity crosses the horizon at different times, bigger inhomogeneities at later times. And this is horizon at horizon crossing. But this is all an idea. For example, one of the ways of generating this, of proving this, is that the ones that I described are quantum fluctuations in the field phi itself. But there are also other quantum fluctuations, gravity waves. And a way of testing this idea would be actually to find gravity waves. In particular, there is a quantity that is called r, little r, and that everybody is trying to measure. And with this relative amplitude of gravity waves with respect to this other type of inhomogeneities, the amplitude in one over the amplitude in the other. And that will give even an indication of this height. There is much to be found about inflation. But this is a separate, it's an add-on. It's a separate deus ex machina in order to explain all the things that you could not explain if you start with a Big Bang, a universe that is expanding adiabatically. You cannot explain many things. For example, the CMB, the horizon at the moment of CMB at this point subtends an angle which is about 2 degrees. I don't remember exactly. It's about 2 degrees. The moon is about half a degree, no? I'm saying something wrong. It's about 1 degree of half a degree. The moon, the size of the moon, just to have an idea. So if one goes at an angle that is a few times the size of the moon, that means that the CMB that is coming from these two places came from completely causally disconnected domains that never talk to each other. They didn't have time. And still, you see that actually you cannot distinguish that. Anisotropies are so small. So how do you explain that? Well, the idea is that all this inflation inflates away an initially homogeneous patch of the universe. And so you have to start, this is one of the problems that actually people who are against, because there are, of course, enemies of this idea, against inflation, says, well, you have to start already from a patch that is homogeneous enough. The only thing is that you are delaying the problem, pushing it back. Yeah, but you push it back in a non-trivial way, because you explain many other things in so doing. But you have to start from a early patch of the universe before inflation, where it is that is already homogeneous, and then the whole thing becomes homogeneous. Namely, you have this type of different values of phi in different regions, and in the whole universe, inside, outside, when there is reheating, the same thing happens. It doesn't matter. And then you are discovering patches of place of the universe that was all contained, all homogenized before inflation. Sorry, this is a very short course, very long but very short course on inflation. Yeah, there is a lot to be said on inflation.
Thank you very much.
So if I may add something to the question, yeah. So just because you asked about what is the thing that makes the fluctuation, right? And as Graciela said, that model is a scalar field. And it's very nice because the scalar field was, let's say, designed not for that. It was designed for accelerating the expansion. And then for free, you compute these fluctuations, and they produce at the end of the story exactly what we see, right? So that's very interesting. But yeah, could be other things. But the point is that the thing that generates the fluctuation, it generates fluctuations in the gravity field, in the metric. So these things, they go out of the horizon, like Graciela say, so they are kind of frozen. And when they come back, they are, again, fluctuations on the density field. So it doesn't matter what produces this fluctuation. This fluctuation will act on the matter that's there. whatever mass is there. So if there is dark matter, if there is neutrino, if there is baryons, whatever that's there will feel this gravitational potential perturbations, right? So this is the imprint that is left. Whatever fluctuation generated, it was kept away, so it didn't evolve, it didn't change, right? And once it comes into the horizon, it starts acting on all matter. And one of the interesting things about the scalar field is that the size, the amplitude of this fluctuation as a function of wavelength. So think of a function and you make a Fourier expansion. So you have amplitude as a function of wavelength. So these kind of things, they are approximately scale invariant. So the fluctuation in the potential, gravity potential, is the same in all scales. So it's a very clear prediction, and that's what we see. So these fluctuations, they enter the horizon, depends on the wavelength. So they enter at different times. They cross the horizon at different times. And this produces the shape of the spectrum that you see. Now, you have these field fluctuations, the gravity field. It will act in dark matter if there is dark matter, and dark matter will feel the potential, right? Because dark matter, we'll hear a lot about possible interactions, but if you think it's just a particle with no other interaction, it will just free fall in the potential. When this acts on normal matter, like a gas, then happens what Graciela said in the morning about the oscillations, acoustic oscillations, right? So gravitational field acting on matter, there is pressure, it goes back. So pressure, gravitational attraction, then pressure, and oscillate. So the matter that feels the potential, how it will react to the fluctuations depends a lot on what's the nature of the matter, the nature of the matter. So dark matter, as it doesn't feel these acoustic oscillations, will start clumping a lot before the normal matter at these scales. So this is something like a very important imprint that for some time, this homogeneity of CMB was great because homogeneous, but it was a problem because how do you have structures? So when they found these fluctuations that we saw the picture in the morning, said, wow, nice, there are fluctuations, great. So we explain large scale structure. But the amplitude of these fluctuations is still small. You need something to be clumping before the matter can clump. We'll hear more about that, of course, but that's, yeah.
So you gain a lot, but I'm not going to talk more about that, except to say that actually you have to start forming structure in dark matter. I will mention that again. Yeah.
So just a basic question. How the neutrinos are detected exactly, like in the experiments?
That's not a basic question. So you have a whole lecture on it, and tomorrow I'll talk a little bit about it. But first, like how anything is detected, right? I'll apologize in advance. I'm a theorist. But the easy things to do is electricity, energy like pressure or heat. So let's focus on one that I know well, electricity. What you do is you build up a very, very fancy pool. You put argon inside. You cool it down so it's liquid. And here's like kind of experience that we are designing at FermLab. One of them, which I'm actually part of it, even if I'm a theorist, it's SBND. So you have a liquid argon inside the detector. Neutrino comes. It doesn't matter because you won't see the neutrino. Let's say it hits argon real hard, produces a muon and a proton. When the muon traverses the argon and the proton, because the muon and the proton have charge, they'll either attract or repulse the electrons in the medium. So as this guy traverses, it ionizes a cloud of electrons. So I have a bunch of electrons here. You still did not detect anything. Now what you do is you do some experimental magic. Don't ask me exactly what is the detail, but you put an enormous electric field such that your electron clouds will drift against the electric field and clock, 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 and get to the top of our detector. We still didn't detect anything. But as they get to the top of your detector, now you put a bunch of wires with some that will basically get these electrons and push them in some way, in some direction. So in a single wire, you see, let's say this is time and this is current. There is always, it's experimental physics. There's always something there. And then eventually these electrons get there and you see like, boom, right? So this signal, a changing current, and current is easy to measure, this signal is what you see from that. Now you have, I don't know, 1,000 wires, you have 1,000 of these plots, you combine them in such a way that you can actually reconstruct this event in 3D. This is one way of detecting neutrinos. But you see, it's very, you go all around because you can't really see the neutrino, so you need to know what the neutrino produces, and then you detect whatever these particles do. This is actually one of the main challenges of neutrino physics because you never see the neutrino itself. And the more, in some senses, like getting a copy of a copy, the more things you have to do to get your final measurement, the worse, the harder is going to be your measurement. Like, in some sense, the neutrino emitted a muon and a proton here, but it's interacting with a nucleus. This proton, before exiting the nucleus, could have hit a neutron or something. So because you cannot see the original neutrino, now you need to understand nuclear physics to know what this actually means, right? So the more steps you have in between, the more stuff you got to understand. But this is one of the ways that you can detect neutrinos. Another experiment is the one in Japan, Super Kamiokande. Completely different, detects light. So what it does is that it's essentially water. Let's say the neutrino emitted a muon, and now this muon emits Cherenkov light in water, which is essentially if the muon travels faster than light in water, right? Because it cannot really travel faster than light. If it travels faster than light in water, it will emit this Cherenkov light to get a bunch of photomultipliers to detect that. By looking at all photomultipliers, how much light they detected, and the time spectrum of the detection, you can reconstruct where the muon came from. By knowing where the muon came from, you have an idea where the neutrino came from and the energy of the neutrino. But you see, it gets more and more indirect. But these are two basic ways of detecting neutrinos. I'll talk a little bit more about that in my next lecture.
Okay, thank you.
Yeah, and next week, Dan will talk more about that. I didn't butcher it, experimental physics, right? Just making sure.
No, but it's nice because we record, so for other people.
Thank you. Just to follow up to that, so when June and either Super or Hyper Kamiokande are kind of compared, what I usually hear is, okay, so Dune is maybe riskier and more expensive, but we're going to gain a tremendous detection advantage using liquid argon over water. Could you maybe explain in a little more detail what that advantage is and maybe how great it is over water?
So on Wednesday, I'll talk a bit about that on the colloquium. So you gotta come. But just to give you like a heads up, if we just take these two things, so this would be the technology of Dune, and this is the technology of Hyper Kamiokande. I can't write that. So Hyper Kamiokande. Just to give an idea, a proton only emits Cherenkov light. Well, any particle only emits Cherenkov light if it's faster than light in water. A proton is only faster than light in water if its energy is about 1.4 GeV. So if you have a proton below 1.4 GeV-ish, it's invisible. So you lose all these particles. So if you're looking at, say, sub-GeV atmospheric neutrinos, which has a lot of physics there, all the protons are invisible, all the neutrons are invisible. You only see the muons and the electrons. Here, it's a little bit more tricky because detecting ionization is very easy. Identifying what is the particle is very hard. But Argonaut, I think it's Argonaut, the Argonaut experiment, which was also a LRTPC but a small one, has shown that you can detect, let me use K, you can detect and reconstruct protons with a kinetic energy above something like, I think it was about 20-ish MeV. So here is a kinetic energy of about 500 MeV. Here is 20 MeV. So you just see way more, right? This is the advantage of liquid argon time detection chambers. You just have way more reconstruction in your events. Now, does that give you a better experiment? Well, it depends. It depends how you use this information. And if you think about it, we are very used to have very little information, either from Cherenkov light or from like less detailed detectors like scintillator detectors. Right now, there is some people looking at how you can leverage this information, but this is a new challenge. Because what you see is just this, right? Imagine that you see this, and then there's a guy here, and then there is something here, and a guy here. Now you tell me what these particles are. And I'll tell you what they are because I drew them. This is a muon, obviously. This is a proton. This is an electron that came from a photon, and this is an electron that came from a photon, and these photons came from a pi zero. Now, you need to see that without me telling you, right? Because this will be data. So until you can do that very, very well, this technology is not going to give you an advantage. So, you know, you have more stuff, you got to work more. I guess it's life. Does that answer?
Yes, thank you.
Next week, you will hear about experiments that go even lower energies that can detect neutrinos. Publicity.
Heard about it.
Hello. So I want to ask you something that you said on your presentation today morning. And I think I just want to confirm because I don't work with these kind of things every day with like gradients and all of that. So when you were calculating the mass contribution to the things, you set 3 steps. You set your Lagrangian, you integrate the W and Z, and the third step was to trace over the background.
Yeah.
And I want to ask you, what is actually this background that you are
Oh,
integrating?
the background, yeah. So the background is essentially, let's say that I'm Fermilab and you are South Dakota.
Okay.
So I emit neutrinos to send to you, but allegedly the world is round. So if the world is round, my beam actually points like this. It cannot point horizontally because then neutrinos just go to space. So it points down, which means that neutrinos need to cross the planet to get to you.
Okay.
And the matter that I'm talking about is the matter of the planet, right? It's like the electrons in the background, like in the dirt.
The background, you mean like the medium?
The medium,
the neutrinos
yes,
are going
like
to.
the dirt or the air
I
or
see.
whatnot.
And when you integrate, you momentum distribution of the protons, neutrons, and electrons, right? But you didn't like put. You suppose that they were distributed like symmetric around the space. Like the question is like, do you use like a spatial distribution that you integrate?
So you can calculate the potential in every point.
Okay.
And as neutrinos propagate, you should like update your potential. Of course, calculating every point is a little bit tricky because you don't want to go to the details that you have one atom here, you have nothing, you have another atom there, you have nothing.
Okay.
Usually, if you deal with any differential equation, the typical oscillation of or rate of change of a differential equation, it's what the function can disentangle. So because neutrino oscillations happen at, say, 100 kilometers or 1,000 kilometers, you cannot disentangle the atomic distance.
Okay.
So you just say it's all constant up to several kilometers, and then you can build up in chunks.
I see.
In practice, the mantle of the Earth is fairly constant, actually. The crust, the density of the crust is fairly constant to the depths that the neutrino traverse. So approximating the entire potential in the whole baseline by a single number is actually not so bad.
Okay, so like if there is like a huge lake or maybe you cross the ocean, it does not change significantly.
It does not change much, although you might want to account for that. But imagine that you have, and I'll talk more about this tomorrow.
Okay.
This is supposed to be the Earth. So this is the core. This is the mantle. And this is the crust, not to scale, right? Because the crust is like super thin, but I can't do that. If you look for atmospheric neutrinos, which is, I have my detector here. I have a cosmic ray that hits the air, produce pions. These guys decay. Eventually, you get neutrinos on it. So these neutrinos, you cross the entire planet to get here. And the density of the crust is of order 2 grams per centimeter cubed, but the density of the core is like 14.
Okay.
This is a big difference. And if you look at the oscillation probability for this changing matter, you actually can see like very, very distinguishable changes on the oscillation probability.
Okay.
So this can be relevant.
Okay. Thank you.
So can you repeat the comment you made about ice cube and matter effects? I think I didn't understand.
Ice cube does not see matter effects. Yes.
Why?
Well, it's just not sensitive enough for that. So you see matter effects if you see oscillations. You need to go to low energy for oscillations. Deep core, actually, right, which is the inner part of ice cube, does see oscillations, but is not sensitive enough to see the details of oscillations with the zenith angle and get the matter effects out of that. Of course, ice cube have seen absorption of neutrinos in the Earth. But that's not a matter effect. That's a hard interaction.
Yeah, but like to see if it goes through the core or something like that, is this?
You need to see matter effects to see that, and ice cube cannot say that there. Ice cube can say that there is a core of the Earth if they go to high energy where they get absorption. So they see that, let's say, 100 TeV to 1 TeV neutrinos, when they come from here, they are not attenuated very much, but when they come from here, they are attenuated very much. So you fit a model of the Earth for that with some density, and you can see the core-ish with ice cube. But that's not matter effect. That's hard interactions. That's absorption.
So the oscillograms that they always put out is not mapped one-to-one to their sensitivity, like in this sense?
Well, no, the oscillograms are fine, but it's like, if you fit ice cube in vacuum, it's not a bad fit. So since I know that you know a little bit more of neutrino physics, if you look for non-standard neutrino interactions, so that is a new matter potential from BSM, there is a term in this matter potential which is called the epsilon EE, which essentially maps into changing your potential to this in the electron side. The constraints on that are actually pretty bad. They become good if you look at scattering, but from oscillation, they're like 30%, 40%. So you are still consistent with no matter potential at all. It's very surprising, very, very surprising.
Hello. You just said that the crust density is 2 grams per centimeter, right?
Sorry?
You just said that the crust density is about 2,
Yeah.
and the core is 14, which is
14
a big
is,
difference,
yeah.
right?
Yeah.
But for the neutrinos crossing the core, don't you have to account also for plasma activity? And your Earth model wouldn't just be a density model?
No, not really. So the only thing you care is density, because it's like, if this was electric charge, you would only care about the total charge at the point that you are. This is not really electric charge, it's weak charge, but the only thing you care is density. What really matters is that, like, we know that the core has a liquid part on it, but we know that from earthquakes. It's actually pretty fun, but I don't have time to talk about that. But the deal is, the liquid core can be relevant for the overall structure of the Earth, But neutrinos really don't care about that. As long as there is a larger density or smaller density, we're good to go. Yeah, there's one there and one over there.
Hello. A question that I have is about the deduction from the probability oscillation. And some moment you assume that the energy of the neutrino is E squared plus equal to P squared plus M squared. And later on, when you're working in a mass eigenstates, you work with a Schrodinger equation. So since I know a Schrodinger equation is a non-relativistic equation.
Yeah,
so
I love this question. This is great. Thank you for asking that. Because I wanted to say something about that.
Okay.
But I'm like, maybe it's going to be just confusing. I'm glad I didn't, and then I was confusing. But so here's the deal. Yes, you should not use the H for non-relativistic particles. What you should do is to use the Dirac equation. Because this is a relativistic field, you have your equations of motion, boom, that's what you should do. So if you use the Dirac equation, you end up with something like this, right? There is this, let me put a J here, and then there is something like this, JK, KJ, neutrino J equals 0. With this, there is a time derivative here. You can say that your neutrino is something like this, and then a plane wave. And if you start with that, you can use the derivative here and like evolve the state. So it's a little bit tricky. Like it happens that if you just use the Hamiltonian, it actually works. But the most correct way to go there is to go from the Dirac equation, derive the equations of motion, get the time derivative here for the dt, take the momentum stuff here for the momenta, and then you can actually derive the oscillation formula. Yeah, but you know, you should not cut the corners that I did to get there.
Thank you.
Regarding the equations you wrote for the neutrinos, we use the same momentum approximation that all these neutrinos have same momenta, but even if these neutrinos are massless, different energy can have different momenta. So what context are we approximating all of them to have same momenta?
Yeah, so if they're massless, when I produce a neutrino by this, let's just take a pion at rest, because anything else is going to be just confusing. I have a muon, and here I have u, mu I, nu I, and there's a sum. If neutrinos would be massless, energy momentum conservation tells you that all of them have the same energy, right? Because the form moment of the pion is this, m pi 0. And now you're decaying that to two particles, everything is set. The only thing that is not set is the angle of emission. So in principle, if neutrinos are massless, all energy and moment are exactly the same, as long as the pion is a plane wave. If neutrinos are massive, they are not the same, but they are fixed, right? You can just solve the kinematics here. You get that the energy of neutrino I is a function of the mass of the neutrino I, and that's it. Well, if you want, the mass of the muon and the mass of the pion, and that's it. So you can actually calculate exactly what is the neutrino energy and momenta. But then the pion cannot be really at rest. There is a localization of the pion wave function. And that actually means that even if you don't want to approximate, you still need to smear things out because of this wave packet. That approximation is actually pretty decent for most of the applications.
But I agree that if all the neutrinos are coming from this pion decay, they should have the same energy. But in general, how can you have, because these neutrino oscillations are for neutrinos coming from space, outer space. So why do you expect them to have the same?
Well, so you won't have oscillations if the system is evolving, right? Like if I emit a neutrino here, and you emit a neutrino over there, these guys have no overlap of their wave functions. They will not oscillate, right? Oscillation is a quantum phenomena. If these neutrinos were emitted from different sources, they will not have overlap enough to give you oscillations. This is very, very unlikely. So usually you consider oscillations for neutrinos that were emitted all at the same time in the same process, like this. You emit one flavor neutrino, which is a superposition of a bunch of mass eigenstates, and that will give you oscillations. So we always assume that production happened for all of them together. And
so
then
the source is same?
Source is not only the same, but the neutrinos were emitted at the same time.
Okay. Because I used to think there's like just a term in Lagrangian, so any neutrino can oscillate to any other neutrino. Doesn't have.
So if you emit like a nu one does not oscillate to anything. You oscillate when you emit, say, a nu one and a nu two coherently as a superposition of waves. And when you emit the two of them, the change in phase, the relative change in phase leads to oscillation.
Okay.
But they need to be emitted together because if not, it's already not a coherent system. Right? It's like if you emit a photon and I emit a photon as we are emitting right now, our photons are not entangled, our photons are not in a superposition because, you know, they are far from each other, essentially. So quantum mechanics doesn't like stuff that is too far from each other. It just behaves classically.
Okay, that gives them more idea. Thank you.
So now I have a question. Is there any physical process that can produce a neutrino in a mass eigenstate?
Well, I have a bad answer. If you emit a neutrino from the Z should emit a combination of all neutrinos to the same amount, so it emits nu 1, 2, and 3 equally, or nu e, mu, and tau, because this state's the same. But I think you're asking something different. You're asking a harder question. I don't think there's any practical. Yeah, so yeah, that's a good point. That's a good point, right? Imagine you do this, right? Imagine yeah, that's a good point. Like, as Graciela is saying, imagine that you emit a nu mu from outer space, very far. This nu mu is a combination of 1, 2, and 3. Because they have different masses, they do have different speeds. So eventually, the wave packet could end up being like this, 1, 2, and 3. Yeah. So in principle, you can separate your wave packets. In practice, this is extremely hard, right? Because the problem is that the sources that will emit this stuff will not emit once and that's it. It's like a supernova. And then you have a gazillion neutrinos over even like over 1 second. It's going to be like a gazillion wave packets on top of each other. Experimentally, you will not be able to see that, right? But in principle, if all neutrinos would be emitted from a supernova at the same time, and your detector made a click, when you detect neutrinos, you could hear either click, 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 or click, 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 right? For normal and inverted mass ordering because of that. It's just that if you emit stuff with some uncertainty, etc., then it gets way harder, but yeah. Thank you.
But I was talking about the beta decay because maybe at the end, the high energy tail of the spectrum, you could produce just one. In
principle, yes. In principle, yes. So in beta decay, beta decay is this, for those of you who do not remember. And if you measure the energy of this guy, the energy of this thing will be, so this is the energy of the electron. It will do this, okay? But then, the energy of this guy depends on the mass of this thing. This thing does not have a mass, so this thing is u, e, I, nu, I. So it actually, in principle, there is an endpoint for one neutrino, there is another endpoint for another neutrino, and another endpoint for another neutrino. So if you measure the real far end of the endpoint, you're measuring only one of them. Now, this is tough. This is tough. Theoretically, yes. Experimentally, Carla will go for it. Experimentally is very, very, very hard. It's like if you take the best experiment that measured that nowadays is Katrin in Germany. And they put a constraint on the effective electron neutrino mass, which is defined as UEI square MI, and there's a sum in I. And this is about smaller than 2 electron volts. But if you remember, the mass splittings were like 2.5 10 to the minus 3 electron volts square. So all neutrinos for them are still like degenerate, and they have not even observed the mass itself. So first you need to measure mass, and then you need to distinguish the masses. So it's very, very, very hard. But in principle, it's possible.
I have one question there.
Professor Graciela, when you were explaining to us how the universe contains all matter, you say that 69% of the contents of the universe are dark energy, right?
Yeah, about, yes, 75, 70, yes, 69 actually, percent, something like that.
And you said that dark energy is related to repulsive gravitational interactions.
Yes.
I was curious, can we interpret this repulsive gravitational interaction as something like a type of modified gravitation laws in which we have, just like the electromagnetism, where you have two types of charges and you have attractive and repulsive forces, right?
Doesn't work exactly like that, because the equations that dictate actually how these things behave are completely different. So you're thinking of a U1 electromagnetism, for example, and then you have charges, positive and negative and stuff like that. Here you have to write down the equations that come from general relativity, either in GR, in which you put essentially one cosmological constant, and then you write down the equation. Essentially, it boils down to, there are two independent equations that come down from these complicated Einstein equations. One is the Friedmann equation, it's called like that, is for how a dot, the scale factor of the universe, the first derivative, behaves. And the second is the A2 dots, which you can essentially associate with acceleration, the acceleration due to gravity. And what happens is that you see that the contribution of matter and radiation comes with one sign that corresponds to being attractive. And then a cosmological constant that Einstein put precisely because of that. So the origin of the cosmological constant is a term added to Einstein's equations because he wanted initially, and when he proposed this, shortly after he proposed the equations of general relativity, he wanted to have a static universe. So precisely he wanted something that at very large scales would make the universe not accelerating in any way. So he wanted A dot equal to 0, A2 dots equal to 0. The second derivative with respect to time equal to 0, and the first also. And so he needed something that would counteract all the matter and radiation that has gravitational interactions that are attractive. So even if you, the Big Bang is understood as an initial condition in which you start expanding. We don't know exactly why. And then from that moment on, the evolution is dictated by the equations of general relativity. Well, so the cosmological constant enters, the contribution to the cosmological cosmological constant enters with a different sign. And what has been seen with supernovas in 1998, there was a very big surprise, because people were thinking Well, they have seen the Hubble expansion, right? The Hubble expansion is a linear term in how the velocity. The velocity is proportional to the Hubble expansion. So the Hubble, a little bit piece of the, so I don't know if here you can see. So if you have a lambda, as I said, all the scales change with the scale factor of the universe, A of t, with respect to whatever you measure now. Huh? You say that this is the way in which a universe that is homogeneous and isotropic. We assume that the universe is homogeneous and isotropic. There is a little bit of an assumption there. We see getting to be more homogeneous and isotropic, and we see the CMB isotropic when we subtract our motion, what we interpret to be a dipole due to our motion with respect to the CMB. So we see that as but the equations are done in an homogeneous and isotropic manner in such a way that the only way in which any interdistance in any direction will change in the same way. So this preserves homogeneity. So now I will, what I will do here is that the lambda dot, okay, any distance, this would be a distance. I can lambda, maybe a distance is better. It's the same. It's any linear dimension, a distance. So here, d dot, I will say, is the velocity with which two things are moving just because of the space-time carrying them around. This would be then a dot, the derivative with respect to time, times d0. But now I replace d0 precisely by a dot over a is d. And here you have the definition of the Hubble constant. This is a distance as function of time, but here you have the velocity is equal to the Hubble constant multiplied by distance. So the Hubble constant is a constant in a space, but not in time. It changes with time. The Hubble constant is usually the present value of what we call the Hubble parameter, which changes with time. And so in distances that are relatively close, then you can find the value of h. What people wanted to know is how h changes. See if the expansion is either slowing down or becoming faster. And so they measure supernovas type 1a. There are several types of supernova. The type 1a are neutron stars that are under the mass at which they would explode, which is a Chandrasekhar limit. And they are getting mass from a companion, giant, whatever, getting mass. At some point, when they get to the Chandrasekhar limit, they explode, and the whole star is destroyed, right? But since they all are destroyed when they have the same mass and they have more or less the same physics, the luminosity is almost the same, is always the same. The intrinsic luminosity, namely the power, the amount of light that is emitted by the star. So when you see them far away, and you know how bright you see them, you can see how far they are. And so you can see how far they are. This is the major point that supernovas type 1a tell you, because then the velocity you can measure through through redshifts and so on. The velocity is measured through redshift of objects that are where this exploding supernova is. And then you measure. And what they measure, what they were expecting to see a deceleration, right? A matter of radiation would produce deceleration. They found acceleration, so the universe is expanding faster and faster. And that means essentially that what dominates A2 dots has the opposite sign to what would correspond to matter and radiation. Whatever that is, this is dark energy. Now there are measurements. The equation of a state of dark energy is simply the pressure is equal to minus the density. So in general, the equation of a state is like this. For matter, for radiation, for matter, the pressure is 0 essentially. For radiation, W is one third, and for a cosmological content, it's -1. And people have been trying to measure, for example, DESI. You know, if you have seen in the newspapers recently, and there was a measurement. Actually, the same thing was done by Planck and so on. What they try is to find a W, they put a W that will be constant, we'll call 0, plus W prime, and here they put, I think, 1 minus A or some variation. With the scale. This is centered at -1, and this is close to 0. Now, of course, these have large error bars. I don't remember the numbers, but the only difference between DESI, and that came in all the newspapers, and the previous type of measurements, is that the error bars, the first sigma, is outside 0. So it measures something with plus or minus, and it would be outside 0. So this is it. But of course, they have only 1 year of data. They have more data now, but they haven't analyzed it, and we will see. So if W is -1, it's measured to be -1, and W prime 0, this is a cosmological constant. And whatever it is close to a cosmological constant. But there are many other possibilities, quintessence, usually, types of fields and so on. In any case, we cannot compute what is a cosmological constant. In the elementary particles, we have associated the easiest thing for a cosmological constant is vacuum energy. So energy has vacuum, right? Vacuum has energy. Vacuum has energy, right? You can measure differences in energy. There is this Casimir effect in which you put two plates and so on, different shape of plates, and you see differences. There is vacuum between the plates and outside the plates, and actually you can, there is a force between the plates. And this is because of vacuum fluctuations. So vacuum fluctuations carry energy, but we can compute them because all our computations give you essentially infinite. This is the problem. We cannot compute vacuum fluctuations. We can compute very reliably. This is the same in quantum mechanics. Probably in quantum mechanics, you have seen in the quantum oscillator, the 0 point, you have to subtract the 0 point because otherwise, 0 point energy, because otherwise you get infinity. So what you compute is just differences. This translates into field theory. We don't have any theory in which we can compute actually the cosmological constant. So this is a problem. So it could be something that changes with time, that we understand as little as we understand inflation, let us say. But no, it cannot be just charges like that. It is something much different, enters into the equations much more different than that.
Thank you.
May I comment on that too? Yeah, so just a very quick comment, but regarding dark energy, right? We use that name, dark energy, to account for the fact that there is this accelerated expansion of the universe, also that the universe is almost flat and you need something besides dark matter, which, as Graciela said, is only like 20-ish%. So there are many reasons that you need something else. This something else we call dark energy, but actually it's, we can later write a very simple equation, but actually whether it's modified gravity or it's another field, at the end, it doesn't make so much difference. One number, as Graciela said, explains everything except these possible indications, right? But until very recently, let's say it explains one number, cosmological constant. Call it modified gravity, call it a vacuum energy that we cannot compute or anything. One number explains everything. But if for some reason this is true, if you have any indication that there is not a constant, then you have to either propose like a new field, and a scalar field is a very simple solution, or you need to propose a gravity that differs from general relativity, But when you write general relativity in a modified way, you say, well, I will not introduce new fields. I will just modify gravity. But modifying gravity is like adding new fields, because in general relativity, you end up only having few degrees of freedom, not all the metric at the end. So when you make a more general theory of gravity, you add new degrees of freedom. So at the end, I mean, there is a big discussion, but at the end you can write like a lot of modified gravity theories, like scalar tensor theories. So, okay, it's a new scalar. Is it modified gravity or new? So it's a very, we can discuss a lot, but like at the end it's not very different. The way you usually modify gravity or the way you usually add fields for dark energy, it's sort of the same, right? But maybe the main point is that we need to find like an observational evidence if there is a change. For now, one constant is like enough. And well, okay, we can discuss more about that, but there is a question here.
The question is for Graciela. How do we know that the universe is more flat than today, and how inflation solves it?
In the sense that the curvature, the radius of curvature is very, very large with respect to what you're measuring. So the curvature that could have been there initially, once you expand enormously, it's like you can see that the equivalence in 2 dimensions is easy, because in 4 dimensions I don't have but in 2 dimensions, right? You have a balloon and you expand it enormously, and then you look at the very small piece. It looks like flat. So this is practically the same idea. Now, how you have to see the evolutions. That I have to show you with equations, actually, that how the way in which it evolves departing from the value of the critical density. So if omega was very small, actually, a very small departure from the critical density, then it will become more. But I have to show you with equations. This I don't think I can explain. If you can explain, I don't know how to explain that without the equations, the proper equations. So you have to write, actually, the equations, these 2 equations that I mentioned, and then you can see that from that point. So you haven't seen cosmology or astroparticle physics before, because this is a course. This would be a completely different course on cosmology, actually, right? But it's.
Yeah, I haven't studied inflation, so I'm kind of touching.
Yeah. This is very important, that whatever departure there would be from, so going forward in time, the expansion of the universe, there will be a departure. So if now is very close, because we measure that in what we measure is the critical, the total density is very close to the critical density. It departs from 3rd decimal place or something like that. Then in the early universe, it was much, much, much closer. And this would become, without inflation, this would be a very odd universe to start with, very fine-tuned. But inflation cures that, because we are looking at a very, very small patch, and so therefore you don't see the curvature, actually. The curvature becomes 0, essentially. Yeah, here is the...
Okay, I'll get this one because it's closer.
Just to be sure, when you show the metrics for the neutrinos, you show the reactor, the atmospheric, the solar, and the Majorana. Just to be sure, this Majorana term has nothing to do with the Majorana fermions.
Oh, no, it does. It does. So the Majorana phases are only there if neutrinos are Majorana particle. Maybe I should have said that, and maybe I didn't. If neutrinos are Dirac fermions, they are not there. You can reabsorb those phases. They are unphysical. I mean, phases are a bit tricky, right? Because you can always put phases here and there. They'll just be unphysical. If neutrinos are Majorana, there are these two extra phases which are not unphysical. You cannot just rotate them away. They have nothing to do with oscillation physics. If you just calculate oscillation physics, they cancel out perfectly. But they can show up in things like double beta decay. When you have this neutrino, neutron, proton, neutron, proton, WW, electron, electron, neutrino. This is a diagram for neutrino-less double beta decay. So if I put the two neutrinos coming out, it's a double beta decay. If they are absorbed, like if an internal line is a double beta decay, neutrino-less double beta decay. When you calculate this diagram, if you just think about it, there is a UEI here, there's a UEI here, and it's not a star because the arrows, they are like this. The arrows for Majorana fermions are a little bit more complicated because usually the arrows will tell you fermion versus anti-fermion, but now it's a Majorana state, so. But the deal is that this diagram will go like UEI square mi of the neutrino here, right? And because it's UEI square, these phases are actually very, very relevant here. They do not cancel out. In oscillation physics, you typically have stuff like U alpha I, U alpha J, U beta I, U beta J, star, star. But the Majorana phases, if you just open up this term, they will cancel between these stars and non-star fields entries of the PMNS matrix here. So the Majorana phases are only there if neutrinos are Majorana. In practice, you don't need to care because if neutrinos are Dirac, you can always put more phases. It's just going to make your calculation like stupid, right? Because you're putting stuff which is unphysical. But the phases are only physical if neutrinos are Majorana, yeah, yeah.
Is that why usually in oscillation physics you'll just see one phase?
Yes. Yes, for oscillation physics, you could add as many phases as you want there, as overall phase and this and that, and they would all cancel out, right? Like, if you think about it, if I have this is a 3x3 matrix, needs to be unitary, but in principle, there could be several phases here, right? You can rephase things out because of quantum field theory. But yeah, like, Majorana phases will not have any impact on oscillation physics at all, so you don't really care. So double beta is actually very, 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 very hard. And the reason is because the lifetime for it to get double beta decay, we don't really know what the lifetime is because we don't even know if that process actually takes place. But normal double beta decay with this is also pretty rare. It's very, very, like if you look, physicists know that because we have measured that, right? This is a background for the neutrino-less double beta. But if you look at like, what's it called, table of elements, chemistry and all that, do you have the lifetime for stuff? They do not even list the lifetime for elements that double beta decay. Because it doesn't matter, right? It's like 10 to the whatever, 10 to the, what, 15 years, 10 to the 11 years or something. It's just so long that you don't really care. Now, Dune is actually not the experiment to see double beta decay. And the reason is the following. The way you measure double beta decay is that first you need to have something that can do double beta, and this is not trivial. So usually, if you have, what is it, Z, and energy. So this is the number of protons, and this is the energy of the ground state for some nucleus. Usually if you have this, it means that, let's say, I don't know, this is argon 40, This is something else which I really don't remember, but you can beta decay down, right? So when you beta decay, one of your neutrons becomes a proton, so your Z number goes 1 up. Double beta decay requires something slightly non-trivial, something like this. Where this guy can beta decay down, that's fine, but this one cannot beta decay here because it would go up in energy. You cannot go up in energy, right? But this guy can double beta. This is why this process is so rare. It's actually, you need to overcome a barrier. But first, you need to have elements that can do that for you. And this is actually not trivial. You need to find these elements in the table of elements, right? It's not like any element that will do that for you. Second, because double beta is your background, you need to measure things like the energy of these guys with great precision. Way more precision than you measure like neutrino energies in Dune. So you need an excellent energy determination and very, very low backgrounds. You're looking at processes which have a lifetime of 10 to the 30 years. So it needs, if you have like 10 events per year as a background, you're dead. So it really needs to be as background free as possible of an experiment. And Dune is just not for that. There is like some crazy idea of getting the fourth module of Dune, doping it with xenon. Xenon has one of the isotopes that does that. And shrinking background somehow, and that's the part that is not very clear, such that the fourth module of Dune could become a double beta decay and an oscillation experiment at the same time. It is a little bit of a Star Trek thing, right? Very futuristic, not really super realistic. But honestly, if people can pull that out, it would be amazing, right? But it's still not obvious.
So I have 2 questions. The first one, going back to the oscillations. So the neutrinos are emitted in flavor eigenstates, right?
Yes.
And they propagate in that eigenstate, in flavor eigenstate?
Well, I mean, they propagate, right? They evolve. If you want each neutrino I with a specific mass, it will get a different phase. If you go to the neutrino, should we do that? Maybe we shouldn't. But the phase that the neutrino gets, each neutrino is like this, right? Mm-hmm. And as we discussed, the energy is slightly different for different masses. So every neutrino, 1, 2, and 3, they will evolve with a slightly different phase shift. So that the phase shift is what causes oscillation.
Okay, so my question is, you emit one flavor of neutrino, right? So, and that flavor can only interact, for example, neutrino electrons, yes, electron neutrinos can only interact with electrons.
Yes.
So do these oscillations also change the flavor? Can they oscillate?
Yes.
Muon neutrinos oscillate into electron neutrinos and then interact with electrons?
Well, so, wait. Okay, so here's the deal. So this is I think the root of this question is on the basis. Mm-hmm. So neutrino physics can become very confusing if you don't get the basis very, very straight in your head. So it's super duper important to define the basis. So the basis of flavor is a basis in which, if you look at the Lagrangian level, a flavor neutrino interacts with a lepton via W, right? Okay. So a nu E, whenever generates something via W, is always an electron. A nu mu only generates a muon. A nu tau only generates a tau. A nu mu, within the standard model, can never generate a tau, ever. But what you can have is to start with a nu mu, let it go, so that the system evolves, and now the system becomes a sum with some coefficients, a superposition of nu mu, nu E, and nu tau. And this superposition could generate an electron, a muon, or a tau, given the oscillation coefficients here. But nu mu's can only generate muons, right?
Yes.
That is the definition of a nu mu.
Yes, perfect.
So yeah.
No, that's okay. I think that's clear enough for me. I had a second question. So how do neutrinos transform under C and P separately? Because we saw that CP and how it can or cannot be violated.
Yeah, we usually don't talk about that for a very simple reason. I think we don't need the planet
And
here.
that's it, I can.
We don't talk about that because imagine that you have, now there is actually an extra complication. Let's say that you have a left-handed neutrino particle, okay? If neutrinos are Dirac particle, actually, if neutrinos are Dirac particle, you will have left-handed neutrinos, right-handed neutrinos, left-handed antineutrinos, and right-handed antineutrinos. This guy here and this guy here, oh, I should be careful. God damn it. Let me call this helicity because that's the only thing that I know. Left-handed and helicity, right-handed helicity. These two guys here, they do not really interact via weak interactions. If they don't interact via weak interactions, you cannot even produce them. If you do a charge transformation, this guy becomes that.
Okay.
Particle becomes antiparticle, helicity doesn't change. If you do a parity transformation, remember, spin, if I put in a mirror, I change these two guys, spin goes back, right? So T and, C and P. We don't talk about that first because we don't even know if neutrinos are Dirac, right? But
Also, oscillations would mess that up, right?
well, even before oscillations, right? Let's just say that you have only one neutrino flavor. So you don't have oscillations, but we don't even know if this state exists. So what we can do is that if you do CP, you transform from what we usually call a neutrino, which is a minus helicity neutrino, to an antineutrino, which is a plus helicity antineutrino. The other states, we have never produced them because they are not produced via weak interaction. We have never detected them. And if neutrinos are Majorana, the only thing you have is this. So the reason why people don't care much about C only or P only is a bit more practical. Like, if I tell you that, I have maybe it's a symmetry, maybe it's not in my Lagrangian. It can't be a symmetry because of interactions. But my helicity minus neutrino, I can map in some other theory to a helicity plus neutrino. So what? I cannot even measure that, right? So I think that is the reason why people don't really care much about C independently or P independently for neutrinos. But in principle, you could apply it. Like these are just transformations. There's nothing sacred about them, except for CPT. CPT is sacred, but the rest, they don't even need to be. The Lagrangian doesn't need to be invariant under charge or parity or time reversal. Indeed, it's not invariant, right? So.
So here you were talking about neutrinos are Dirac particles. But in the standard model where neutrinos are massless particles, they are Weyl particles. You only have two states, an antiparticle with a helicity state and a particle with a helicity state. In that case, how do you make the CP violation to produce the oscillation? In that case, you don't have oscillation, no?
Yeah, so the standard model for neutrinos, okay. So first, one thing that some people do not even agree, but I do, is that the standard model is with massless neutrinos. To me, that's the only definition that makes sense, because in the standard model, I want to put only particles that I have detected.
Yeah, of course, because you don't have right neutrinos, then you don't have a Yukawa coupling term.
Exactly. So if you do not have this field, and if you do not have anything extra, then neutrinos are actually massless. and then neutrinos do not oscillate, and that's ruled out by like 20 sigma. So neutrinos do oscillate, which means that neutrinos need to have a mass.
Of course.
Of course that we don't know where this mass comes from, and for oscillation physics, in many mass models, this is completely irrelevant. As long as neutrinos have a mass, they will oscillate the same way. But, you know, if the mechanism that generate neutrino masses is not at a super high scale, it's at a lower scale, you could actually see imprints of the neutrino mass generation in neutrino oscillation experiments. Maybe Mateus will talk more about that.
Okay.
This is one of the open questions of the Standard Model, right? Like, how do you actually generate neutrino masses?
Yeah. So also you talk about the T violation in the case, for example, of the oscillation to muon neutrino to, for example, to electron neutrino to muon neutrino. Can you explain a little bit more about that?
Oh, it's just that if we take this process, a nu mu going to a nu e, and we apply T, we get a nu e going to nu mu. That essentially means that these oscillation probabilities here should be, if T is conserved, these oscillation probabilities should be identical.
Yeah, it's symmetric to
They do not
time
need
reverse.
to be conserved, right? T does not need to be conserved because the only thing that needs to be conserved is CPT. If CP is violated and T is violated by the same amount, you still get CPT invariance.
Yeah.
But in some sense, there is something special about the T channel compared to the CP channel, if you think about it. When we produce neutrinos in the Earth is matter. If we try to do a CP transformation to our process, you can change your neutrino to an antineutrino, and that's fine, that's CP transformation, but you can't change the Earth to anti-Earth. So the CP transformation for a physical process that is being measured experimentally is never perfect. You always have, let's call it a contamination of CP violation because the Earth is matter, not antimatter. T is not the same because this is nu mu going to nu e in a background of electrons, and this nu e going to nu mu in a background of electrons. So this actually, if this probability is experimentally, if you measure them to be the same, you know that T is actually conserved, CP is conserved, all good. These ones here, even if CP is conserved, the matter effects will make them slightly different. So in some sense, this is a little bit more clear, like more clean to measure CP violation or T violation. It's just hard to have a beam of nuis. Very, very hard.
Yeah. And last question, how can you guarantee there is energy conservation in neutrino oscillation? I mean, when you are changing, for example, from electronic neutrino to muon neutrino, you have to change the mass. And also, if you are going to, you know, to guarantee there is energy conservation, then you should have like a momentum change, no? How can you guarantee that this is happening?
So I can guarantee energy conservation on neutrino oscillations, and I mean it. I can't guarantee it because I wrote the Lagrangian. My Lagrangian conserves energy, therefore everything conserves energy. Experimentally, that's a different business, right? From a theoretical point of view, if my Lagrangian has energy momentum conservation on it, if you use the Nether theorem, right? Just a Lorentz group and all that, then necessarily everything will conserve energy. So energy conservation from a theory level is guaranteed when you write a Lagrangian.
Yeah, but
experimentally, then it's a big deal,
yeah,
right?
I
It's
mean,
not obvious.
in your Lagrangian, you are setting a term that produces the neutrino oscillation, or is it Lagrangian that requires the beta decay, for example, that what you were talking about, the matter interaction, the interaction with the matter.
So in my Lagrangian, I have all interactions between neutrinos and everything.
Yeah, but I mean a neutrino, you know, in a free Dirac field, for example, and your neutrino oscillates. And how you can be sure there is energy conservation in that process, you know?
Yeah. So let me make. This is why I don't like to talk about flavor neutrinos, because they become very confusing. Like, what is the mass of a nu e? And when you oscillate, oh, but now this nu e became a nu mu, where this mass came from, the mass of the nu mu. And the reason for all these questions is because nu e does not have a mass, nu mu does not have a mass. These are not real particles. So you should understand this, at least the way I like to understand this, in a simpler way. When you produce neutrinos, what you produce is always a combination of this. For example, you produce a combination of nu 1, 2, and 3, and that's it. And when you detect maybe a combination of nu 1, 2, and 3. So you produce a nu 1, you detect a nu 1. That's fine. You produce a nu 2, you detect a nu 2. The coefficients of detection will tell you the flavor. But that's just a rate argument. If I produce a nu 1, is a nu 1. The fact that is in a quantum superposition with another state or not, it's irrelevant for energy conservation. If I produce a nu 1, it is a nu 1 with some energy, and I detect that energy. We're done. So in some sense, you're not changing masses. You're only changing phases. When this nu, let me just do 2 neutrinos, right? I produce cos theta nu 1 plus sine theta nu 2. When this state evolves, let me not put a phase on nu 1 here. This will just evolve to some I phase sine theta nu 2. And, well, let me just write this back. Cos theta nu 1, right? So this is neutrino at the time t equals 0, and this is a neutrino at the time t not equals 0. This is the only thing that is happening. It's just a phase that is changing. There is no extra mass. The particles nu 1 and nu 2 are still nu 1 and nu 2. But because of the phases, the probability of detecting this neutrino by producing an electron is different from detecting this neutrino by producing a muon. That is to say, the probability that you detect this neutrino after it evolves as a nu e or a nu mu is different. But nu e's and nu mu's are not particles. If you try to apply like energy momentum conservation to nu e's and nu mu's, you're going to go crazy because they do not have even mass, well-defined mass. Does that make sense?
No, but the thing is that how you can work at the same time with the neutrino oscillation, and you can set the Lagrangian in the standard model setting like neutrinos are fields, and those fields you can say that are particles. How you get work at the same time with both ideas? You mean there is like a there is a problem in the idea of working with this and this,
So the problem really is to try to think about neutrino flavor. I do not care about neutrino flavor. There is no flavor states, right? Let's forget about flavor completely. I can write my entire Lagrangian as a function of nu 1, nu 2, and nu 3. And I produce a combination of these guys, and I detect a combination of these guys. And that's it. The oscillation physics comes from the fact that when I produce a state, combination of 1, 2, and 3, with an electron, I can actually detect the state after it propagates with a muon. And that's because the phase changed. So the way it couples to the W changes. But energy momentum conservation is still there. The masses have always been M1, M2, and M3, right? There's no mass changing. It's just a phase on a system. So it's all kosher, as long as you work with real particles, which is the mass eigenstates. If you try to go to flavor,
can I say
it's
something?
confusing.
You're the expert, but since I'm a non-expert who has dealt with this on my own, and because everybody who understands quantum mechanics has to start working in neutrinos, and then you realize you never understood quantum mechanics in the first place. This is what happens to everybody. So what is conserved is energy momentum. It's a 4-vector. Mass is not conserved in a reaction.
That's true.
Energy momentum is conserved.
Yeah, but
so you
in
have
that
to
case,
think always in this. The basis that you use doesn't change that. It's always energy momentum that is conserved. Mass is not.
Yeah, but
mass is changing all the time.
You can change momentum in that case because otherwise that would mean that you have a scattering process that change the momentum of the particle.
But you can change the mass without changing the momentum. This is the point.
Yeah,
the energy momentum.
Where does it come from?
The energy momentum will be conserved.
You need energy to change your mass. if you are increasing your mass, you need to take energy from the medium.
But
the
just do this, right?
Yeah.
I have only one neutrino, so I produce new one, I detect new one.
I understand that.
Then I produce new one and new two. I detect either new one or new two, but actually what I detect is some combination of them. So there's no problem with energy momentum. It's just that flavor states are very confusing.
But this happens, I don't know if you are confused by the fact that, for example, so mass is a very complicated subject. What is mass? What is mass? What do you think mass is, to start with? Because mass is something very complicated. When we start thinking of mass, in Newtonian mechanics, you just say, well, this is the quantity of matter. But what? Then you go to go to special relativity, and you say, well, mass is only energy at rest. Otherwise, it's a form of energy, right? It's not. And then you go to, for example, quantum mechanics, and you have that the mass of a nucleus is smaller than the sum of the mass of the nucleons that are inside. Isn't that so? The mass of a nucleus is stable because its mass is smaller than the sum of the masses of the nucleons that are inside.
Yeah, but you have interaction there.
Sorry. The discussion is really, really interesting. However, we have to keep time. So in the interest of time, I will stop this discussion now.
Sorry.
We have 30... We have 30 minutes of general questions in the afternoon, so we can continue that. We also have time for discussions after the after discussions during refreshment. So you have plenty of time to clarify everything. The discussion is very interesting. So before we break for lunch, I have two announcements. So the first, if you are presenting a poster and you didn't send the one slide yet, please do so before the end of the afternoon, not the day. So don't send it in 23 hours.
Up to 20 is okay.
So 8 p.m., pay attention please, 8 p.m. is the time limit for you to send your one slide about your poster. Maybe you present your poster on Thursday, that's fine, but send us your slide today. So if you present the poster on Wednesday, send us the slide today. So if the slide doesn't get to us until 8 p.m., it means you don't present the slide, the poster. You can hang the poster there, feel free, but you don't have the certificate that you presented the poster, okay? So if you have a poster presentation and you need some certificate that you presented your poster so that you get paid for your trip, please do send your one slide before, because in English we say by 8 p.m. By 8 p.m. is not like approximately 8 p.m. It's before 8 p.m., okay? And, regardless of any funding, if you want to show your slide, your poster, which is nice, it's just an advertisement. It's not a formal presentation with questions. You just have one slide and you make publicity. You make it the way you want, okay? It's a free 2 minutes, 3 minutes, free 3-minute time of publicity. You do the publicity the way you want. But your poster is considered a poster presentation if you do that. If you don't send your slide, you don't do that, you don't have a poster presentation, feel free to hang your poster there. Very nice, no problem, okay? First announcement. Second, please don't forget to sign the presence sheet. We are circulating it for the afternoon. In the morning, we were missing one of the sheets, so your names after V were not there. This has been solved. However, there are some people that have not registered or are not in the registration list. So if you didn't register for the school, but you're signing up the presence sheet, come to talk to us, right? Because we have to have you registered for the meeting. I think that's the last announcement. Anything else from the organizers? Okay, great. So now we can go for coffee break, but we'll be back at 4 p.m., okay? So 20-minute coffee break. Thanks.
Are different.
Morning and afternoon.
Oh.
All right, let me sign this one. Posso pegar essa caneta? Na borda? Eu posso assinar à tarde? Tá, pera. É sua, né?
Sempre vai lidar, os seus pagamentos sempre são contados a fila. Então, isso aí tem sempre essa confusão que o pessoal fala, o Neutrino, ele é em fila, ele não tem fila, porque esse Neutrino não é instalado em volta. Isso aqui é apenas uma expansão lagrangiana com ação, que você fez uma conta e pronto. Você vai interpretar o Neutrino, ele é em e ele se absorve em tempo zero. Para mim, isso só confunde a cabeça. Então, isso aqui é ridículo. Isso aqui eu acho que é muito pequeno, porque você teria, imagina, cada vez que você coloca um fórum de WZ, você tem um propagador aqui sobre a massa, você ganha defer na amplitude. Essa amplitude já vai para o defer quadrado. A seleção de operamento vai para o defer quadrado. A combinação desses dois tem dois modelos de defer a 6, que é a negociação de produto. Você vai quadrar isso a probabilidade da causa. Ou multiplier. Se você pode conseguir medir no multiplier, é coisa assim, né? Às vezes, eu poderia fazer isso aqui no multiplier. Neutrino, heavy neutrino, por exemplo, e aí decai, que é a célula de pouco decai. Onde o heavy neutrino é um cara que está relacionado com a massa de neutrino.
Pô, verdade, né?
Possivelmente.
Você foi nerd.
Mas medir isso aqui no